In the quest to slow biological aging and protect cellular integrity, few nutrients have garnered as much attention as vitamin D and omega-3 fatty acids. Both are widely recognized for their systemic health benefits, from reducing inflammation and supporting cardiovascular function to modulating immune responses and improving mood. But when it comes to protecting DNA, particularly telomeres, the fragile end caps of chromosomes that determine cellular lifespan, their effects may not be equal. In clinical trials where both were administered, researchers found that vitamin D supplementation appeared to offer protective effects on telomere length, while omega-3s did not show the same outcome. This unexpected difference has sparked important questions about their mechanisms, bioavailability, and how each interacts with the cellular aging process. The telomere is a sensitive structure, constantly exposed to oxidative stress and inflammation, both of which accelerate its erosion. Nutrients that mitigate these stressors are often expected to benefit telomere maintenance. Omega-3 fatty acids, particularly EPA and DHA, are well-known anti-inflammatory compounds. They improve lipid profiles, reduce systemic inflammation, and lower C-reactive protein levels. On paper, this makes them ideal candidates for telomere protection. However, in practice, their protective effect on telomere length has not consistently been demonstrated in human trials. This doesn't mean they lack benefit altogether. Rather, it suggests their mode of action may not directly influence telomere stability in the same way as vitamin D does. Vitamin D, by contrast, appears to have a more direct relationship with genomic health. Its active form, calcitriol, binds to vitamin D receptors, VDRs, present on many cell types, including those involved in immune function and DNA repair. When activated, these receptors trigger transcription of genes responsible for reducing inflammation, enhancing DNA repair mechanisms, and possibly upregulating telomerase, the enzyme that rebuilds and maintains telomeres. In this context, vitamin D acts not only as a hormone but also as a genomic regulator, influencing the aging process at a much deeper level. One possible explanation for the disparity between the two nutrients in telomere outcomes lies in the timing and duration of their benefits. Omega-3s may exert their anti-inflammatory effects in ways that are systemic and chronic, meaning their influence is broad but slow-acting and less targeted. Vitamin D, especially when a deficiency is corrected, may trigger a more immediate restoration of immune and cellular repair functions, leading to observable differences in telomere dynamics over shorter time frames. This could explain why, in certain trials, the benefit of vitamin D was statistically detectable while omega-3s appeared neutral. Another factor is the interaction of vitamin D with telomerase itself. Some studies have shown that vitamin D may help preserve telomerase activity in leukocytes, white blood cells that play a crucial role in inflammation and aging. This connection is particularly relevant since many telomere studies measure telomere length in leukocytes as a proxy for systemic aging. Omega-3s, on the other hand, do not appear to influence telomerase directly, which may limit their effect on telomere length, despite their other health-promoting qualities. It is also worth considering the bioavailability and dosing differences in clinical studies. Omega-3 absorption can vary widely depending on the form used, triglyceride versus ethyl ester, the presence of cofactors like fat in the meal, and the individual's metabolic state. In some cases, trial participants may not have achieved a therapeutic dose sufficient to alter telomere biology. Vitamin D, when supplemented in adequate amounts and monitored via serum 25-OH-D levels, tends to have a more predictable pharmacokinetic profile, allowing researchers to better measure its impact on biological markers. Moreover, vitamin D deficiency is incredibly common, especially in populations with limited sun exposure or chronic disease. Correcting a deficiency can lead to substantial biological improvements, including improved immune modulation, lower oxidative stress, and enhanced mitochondrial function, all of which contribute to a more favorable environment for telomere maintenance. Omega-3s, while essential, are not as commonly deficient in a clinical sense, particularly in populations with some dietary intake of fish or fortified foods. This difference in deficiency rates may have influenced baseline telomere vulnerability and the measurable impact of each nutrient. It's also important to frame this discussion within the broader concept of synergy. Nutrients rarely work in isolation. Vitamin D and omega-3s may have complementary effects that are more powerful when combined, even if only one shows statistical significance in a given trial. For example, both have been shown to reduce the incidence of autoimmune diseases, cardiovascular risk, and depression, all of which are linked to biological aging. While vitamin D might directly influence telomere length, omega-3s could help preserve cellular environments where vitamin D and telomerase operate more effectively. In this view, omega-3s may act more as enablers than as direct telomere protectors. Ultimately, the fact that vitamin D shows a more consistent benefit for telomere maintenance does not diminish the value of omega-3s in a longevity-focused lifestyle. It simply highlights the specificity of nutrient functions. Vitamin D appears to have more precise genomic actions that impact cellular aging, while omega-3s offer a broader, anti-inflammatory foundation that supports whole body health. Their roles are complementary, not competitive. Each fills a different niche in the intricate mosaic of aging prevention and health optimization. As research continues to evolve, future trials may better clarify how dosage, form, duration, and individual variability affect these nutrients' influence on telomere biology. For now, the takeaway is not to abandon omega-3s, but to recognize the special genomic role that vitamin D appears to play in preserving DNA integrity. Combined with other strategies like sleep optimization, exercise, stress reduction, and a nutrient-dense diet, both vitamin D and omega-3s remain essential tools in the effort to maintain biological youth and delay the onset of age-related disease. In the end, vitamin D's unique ability to activate genes involved in repair and cellular protection gives it an edge in influencing telomere biology. But omega-3s still support the overall biochemical environment in which healthy aging can occur. It's not a question of which is better. It's a matter of understanding how each fits into the much larger system of aging well from the inside out.